Welcome back to Algorithms and Uncertainty. In the last lecture, we introduced the problems of two-stage optimization, where we have one stage in which things are cheaper, but we don't actually know what we'll have to do. And then we have a second stage in which we actually know what we'll have to do, where we know what we'll have to cover, but then things are more expensive. Today, we'll consider the Steiner tree problem in this two-stage model. So, what does this mean? First, we do not know which terminals will have to be connected, but we only know a probability distribution. Then, in the second stage, we know which of the terminals have to be connected, but the edges are more expensive. So this is, again, a different version of the Steiner tree problem under uncertainty. Recall that we've already seen the Steiner tree problem as just the online problem without any prior information, for which we had this O of log k competitive algorithm. Then we also discussed the problem in which we knew in advance which probability distributions the terminals were drawn from. And then we got a constant competitive algorithm. Importantly, in both cases, the point of comparison was the offline optimum. This is different today. Today, like last time, we're again comparing ourselves to the optimal policy. So the optimal choice that you can do when you also in the first stage only know the probability distributions. A comparison to an offline optimum in this two-stage optimization does not really make sense, because the exact point of two-stage optimization is that in the first stage you know less than in the second stage. So an offline optimum would already know everything in the first stage. Good. So let's first recap what we know about the Steiner tree problem. What's the Steiner tree problem? The offline problem is we have a graph which consists of vertices and edges. We have edge weights, and we have one root vertex, and we have a set of terminals. Now, what's our task? Our task is to find a subset of the edges such that all terminals are connected to the root using only the edges in this subset of the edges that we selected, and our goal is just to minimize the sum of the edge weights of the edges that we choose. Let's also recall what techniques we can use. We can, without loss of generality, assume that this graph is a complete graph and that the weights fulfill the triangle inequality. Why can we assume these things? We can assume these things because effectively we could replace any vertex, any edge by a shortest path, and shortest paths are only easier or make a solution only more valuable in a sense, because we are connecting just more vertices than if we choose direct edges. So this is why also today we will be making these assumptions, and under these assumptions we have these comparisons between a minimum spanning tree and an optimal Steiner tree. A minimum spanning tree, we're now considering the graph restricted to only the root and the terminal vertices, and given that this is a complete graph, we can now, this is also still connected, and there we can now ask what is the minimum spanning tree of this graph. This minimum spanning tree is a feasible choice for a Steiner tree, but it might be more expensive. Why can it be more expensive? Because a Steiner tree might also use vertices for the connection which are not terminals, the so-called Steiner vertices. And therefore, we have that the minimum Steiner tree solution is at most the cost of the minimum spanning tree solution of this graph, where we're restricting all the vertices to be only the terminals. But, and this is something we've also seen before, this is only within a factor of 2. So Instead of solving the Steiner tree problem, we can also solve the spanning tree problem and lose only a factor of 2, which will, by the way, be enough for our purposes today because we are just losing constant factors and we are fine losing constant factors. Cool. Now what we want to do is we want to turn this into a two-stage problem. We now want to turn the Steiner tree problem into a two-stage optimization problem. And how will this work? Well, in the first stage, we do not know which of the terminals will actually have to connect. We only know a probability distribution. And then in the second stage, we know which terminals will have to connect, but the connection costs are more expensive. And more precisely, this looks as follows for this problem. So in the first stage, the terminal set T is unknown, and we know only a probability distribution. And we can add edges to S at a cost of WE. Then in the second stage, T is known, and we can add edges to S at costs lambda times W, where lambda is just some factor which is at least 1, which is an inflation factor. And now the expected cost of a policy is, of course, how much? Take the sum over all edges which are selected in the first stage, WE plus the expectation of take the sum over all edges which are selected in the second stage, and then we'll have lambda times WE. So this problem is very similar to the set cover version that we've seen before. So we'll also have two stages. In the first stage, we don't know what to cover. In the second stage, we know what to cover. What is different now is that we have this uniform inflation factor, lambda, which is at least 1. In the set cover problem, or in the two-stage set cover problem, we had that the first stage costs and the second stage costs were arbitrary. Now we just have that everything that costs WE in the first stage costs now lambda times WE in the second stage. So if the cost is 5 in the first stage, it will be lambda times 5 in the second stage, and so on. Good. But what will still be the same is that we are interested in finding or approximating an optimal policy. So this is still a Markov decision process, a huge Markov decision process. So we certainly cannot hope to find an optimal policy. But what we can hope is that we can find a policy which is close to the optimal policy. And this is something that we want to do in polynomial time, of course. And what should this look like? Well, if lambda is, say, 1, then there's really no point in using this first stage. If lambda is 1, then all you can do in the first stage, you can also do in the second stage. But if lambda is huge, then suddenly you want to be covered for everything that can happen in the second stage, because in the second stage, actually everything is unaffordable. So if lambda is infinite, then you might maybe just choose more or less all edges of the graph, so that whatever terminals now show up, they are just covered. One important thing that I'd like to mention now is that this probability distribution, this is just one probability distribution over sets. And it is not that we have like independent or probabilities for or independent events, whether this or this terminal now shows up or something like this, like what we had in the online problem with probabilistic input. Nothing like this. So T, this is just drawn from one probability distribution. Of course, you can also assume that you have a certain probability for every vertex to be actually active and so to be part of this terminal set T, but you can also have much richer settings where T now is just drawn from some arbitrary probability distribution. Good. So what's our point of comparison? I already mentioned this, that we are comparing ourselves to the optimal policy. Let's once again write this down. So what we'll now say is that E star 0, this is the choice of the optimal policy in the first stage, and E star T, this is the choice of the optimal policy in the second stage if the terminal set is T. And our benchmark, so what we'll be comparing ourselves to is what I'll call Z star. This is exactly the expected cost of the optimal solution, of the optimal policy. So the sum of the first stage edge weights plus the sum of the second stage edge weights, they are all multiplied by lambda. Let me once again say that this is not the offline optimum. The offline optimum, what would that do? The offline optimum would already know in the first stage what terminals it will have to cover, so it will only choose edges in the first stage and nothing in the second stage. But the exact point of this problem is, well, you do have some uncertainty in the first stage, there you can do things, but then you can also do things in the second stage. And the question is, how do you balance your choices between the first and the second stage? And for this problem, we'll see a very simple algorithm which approximates the optimal policy. It will not use linear programming, but instead it will just be very combinatorial. It will look very similar to the algorithms that we saw for the Steiner tree problem so far. Namely, what we'll do is we'll draw from the known probability distribution a couple of times, and this tells us what to cover in the, or what to connect in the first stage. And then we hope that having done this, we are well prepared for the second stage for whatever can come there. More precisely, the algorithm looks like this. It is called boosted sampling. And what we do is, in the first stage, we draw lambda times from the distribution and we'll call the outcome S1 through S lambda. And then we'll set E0, which is our approximation of what the optimal policy does in the first stage, or what is actually just our choice for the first stage, is just a minimum spanning tree on R union S1 through S lambda. I should mention here that I assume that lambda is an integer. Actually, you can also do these. You can also use this algorithm as lambda if lambda is not an integer, but things get a little more complicated. Cool. So now we have our first stage choice. And let's now talk about the second stage choice. In the second stage, we'll set the weight of edges to 0 for all edges which we have already chosen in the first stage. Then we'll set ET to a minimum spanning tree on the actual terminals, but of course we don't have to choose the edges which we took already in the first stage. Good. So this is actually a very simple algorithm. How long does it take to run it? We'll have here lambda plus, or here we'll have lambda times that we draw from a probability distribution. And then we run a minimum spanning tree. Then here we also compute another minimum spanning tree. And the point is, of course, if lambda is polynomially bounded in the input size, then this will be a polynomial time algorithm. And what we hope is that actually the expected cost that we incur this way is close to this Z star. Z star, this is the expected cost of an optimal policy, which will be NP hard to compute because it in particular has to be able to solve the Steiner tree problem. And indeed, what we'll be able to show is the following. We'll be able to show that the expected cost that we pay in the first stage plus the expected cost for what we pay in the second stage. There, of course, costs get multiplied with lambda. This will be at most 4 times Z star, where Z star is just the value of the optimal offline solution. So we have a 4 approximation to the optimal policy. And what do we do? How do we prove this? we'll show that on the one hand, the costs of the first stage are bounded by 2 times the star, and we'll also show that the expected costs of the second stage are bounded by 2 times the star. And in combination, this exactly gives us what we want, namely if we just add up the two, then we have this guarantee. One thing that strikes me as important here is that whereas in the set cover we were comparing the first stage cost to the optimal first stage cost, the second stage cost to the optimal second stage cost, this is not what we're doing here. We're comparing what we're getting in the first stage to a constant factor times the cost of the overall optimal policy, and also what we're doing in the second stage to the overall optimal policy. And this is exactly what we want to do now. We'll first talk about the first stage, and then we'll talk about the second stage, and in both cases we'll show this factor too. Let's now talk about the first stage. How did this first stage work? Let's maybe go back to our algorithm. Our algorithm said, okay, we draw lambda times from the probability distribution. We call that now the outcome S1 through S lambda, and we take E0 to be a minimum spanning tree on which connects all these terminals that we've just drawn in all these lambda draws. We connect all of them to the root via just one minimum spanning tree. And what we're claiming now is that the expected cost that we're incurring this way is at most 2 times the cost of an optimal policy. And why is this true? This is actually pretty simple to see. If you find the correct notation. Well, consider E star 0 union E star S1 union and so on union E star S lambda. What does this mean? Here, this is the first stage choice of the optimal policy. And now this is the second stage choice of the optimal policy. If the terminal set is S1. Good. Now, of course, the terminal set can be S1, it can be S2, it can be S3, it can also be S lambda. All these are possible sets of terminals which the optimal policy has to be prepared for, because this is exactly where these sets come from. We are drawing them from the distribution. So this is what do we know about this? This is a feasible Steiner tree connecting all of S1 union S and so on up to S lambda to the root. And what are we doing in our first stage? In our first stage, we are actually taking a Steiner tree, which connects all of S1 through S lambda to the root. So what we now have is that the weight of our choice for the first stage, which is nothing but a minimum spanning tree on S1 through S lambda, this is nothing but the cost of a minimum Steiner tree, or 2 times the cost of a minimum Steiner tree, connecting all of them. And now what is the expected cost of, or what's the cost of a minimum Steiner tree connecting S1 through S lambda to the root? Well, this will certainly be at most as much as when we're taking now, this is what we now identified as one possible solution to that. So instead we could take S1 through S lambda E. We'll take these sets here. This is a possible solution to this, and I shouldn't forget the factor 2 in here. Now, how expansive is this? What is the weight of the first stage cost of the optimal policy, and then the second stage choice of the optimal policy when the terminal set is S1, and so on? Well, this is certainly no more than add up the first stage cost plus add up all these second stage costs. Why isn't this equality? Because here it might happen that we have an edge multiple times. We have it in multiple of these sets. Here, then we'll have to pay for it multiple times. Here we'll have to pay for it only once. But this tells us now the following. This tells us that the expected cost that we have now for our first stage is at most 2 times what the optimal policy pays for the first stage, plus 2 times, take the sum from 1 through lambda, the expected cost of what the optimal policy would have in the second stage when the set is of terminals as Si. And now there's one crucial thing, namely, where did our Si come from? Our Si was drawn from the exact same distribution that T will be drawn from. So instead we can say, okay, the expected cost that the optimal policy will have for the second stage when the terminal set is Si, this is exactly the same as when the terminal set is T, just because Si and T are drawn from the same distribution. So we might as well write this now as 2 times the cost of the optimal policy for the first stage plus 2 times, now we'll have this sum here, the expected cost for the second stage. And what we'll see here is, okay, this is actually just lambda times that thing. So we'll have 2 times the cost of the first stage plus expectation of lambda times the weight of the edges chosen in the second stage. And this here this is nothing but Z star, this is nothing but the cost of the optimal policy. So this proves this lemma that the expected cost of our first stage choice is no more than 2 times the cost of an optimal policy. I think this is actually remarkable that this works because somehow we are comparing ourselves to what the optimal policy does in the first and in the second stage, although we don't actually know what it will be doing and how things split up. The only thing is we know that, okay, if we are drawing or lambda times from the distribution, this is what the optimal policy definitely has to be covering. And so this is why we can compare ourselves to this. Of course, our costs are now much cheaper than what the optimal policy has to pay for the second stage. And this is exactly the reason why we can draw multiple times from the distribution and cover all of this. So even when we're not drawing multiple times, lambda times we're drawing from the distribution, and still this will just not be too expensive, because somehow in the first stage we're allowed to spend even lambda times as much as what the optimal policy is spanning, or we may choose somehow, if all edges were costing the same, we were allowed to choose lambda times as many edges as the optimal policy is choosing. Cool. So far this is extremely elegant. I hope you realize that this is somehow very similar to the argument that we used for the case of online Steiner tree with known probability distributions, although here so far it is a little simpler, although it's also a little smarter so far because we had this boosted sampling that we're drawing multiple times and not just once. But what of course is now still remaining is, how expensive is the second stage? Let's now talk about the second stage. And before we get there, let's first recap what our second stage of our algorithm looks like. The second stage of our algorithm, we set all the edge weights for edges that we chose in the first stage to be 0, and then we are computing a minimum spanning tree on the new edge weights where we modified the edge weights accordingly. And of course, we don't have to again choose the edges that we chose in the first stage. Of course, this minimum spanning tree is probably very likely to take them because they cost nothing. So the minimum spanning tree will certainly take everything that we took in the first stage and then to choose some other things to make sure that everything is connected. And what do we now claim? We now claim that the expected cost of the second stage, so lambda times the respective edge weights, is at most 2 times the cost of the optimal policy, or 2 times the expected cost of the optimal policy. And how do we do this? What we'll have to be talking about is how expensive is it to augment a spanning tree, which means we so far have some kind of a spanning tree because our first stage choice was a spanning tree already. And now we have some further terminals, which we also want to connect to this. And to this end, let's introduce the following notation. Let A and B be subset of the vertices, and now we let delta of AB be the cost of a minimum spanning tree on the graph, we now have the root at vertices A and the vertices B. When we set the weight of edges to be 0 for all U and V which are R or in A. So the way we can think about this is we have all vertices V. And within that we have some vertices A. Let's also say that R is within A. And then we'll have some other vertices B. Now here within A, connecting everything is for free. So all that we have to do is that we'll have to connect everything inside B, which is not inside A. This we will still have to connect somehow to A. But the way we're phrasing this is we're computing a minimum spanning tree of all of A union B, but edges inside A are free. And now we'll have the following property, namely that for any U1 through UK, which are a subset of V, we have the sum of delta of the union of all uj except for an 1i and ui. This is at most the weight of a minimum spanning tree on U1, on the union of U1 through UK. So this is a little more complicated than what we have here, because now we might have, well, let's start with two sets, U1 and U2. Then this would look something like this, where we wanted to connect B to A. But then we are also considering the reverse situation where we want to connect A to B. So this is exactly what we're writing down here in this formula, namely that we want to connect UI to all of to the other sets UJ, so all UJ except for UI, inside them the connections are for free, and so we only want to now connect UI to these other sets. And we're taking the sum over all I from 1 through k. So each set UI gets, or each of these k sets gets to be the set UI exactly once. And we now say, okay, this we can upper bound by the cos of a minimum spanning tree. And how do we prove this? Well, to be honest, we've already shown a special case of this, namely for the case that these U's were just singleton sets, in the case where we had the for the problem of online Steiner tree with known probability distribution. There we were only saying, okay, how expensive is it now to connect vertex UI to the other UJ? And therefore we can actually do the exact same argument. So what we'll do is we'll consider the minimum spanning tree of U1 through UK as a rooted tree with root R. And for every vertex, we can now let AV be the weight of the edge connecting V to its parent in the tree. And what we now have is that delta of the union of all uj comma ui is at most take the sum over all vertices ui take away uj take away the union of all uj av. This looks super complicated and super intimidating, but the idea is truly simple. So what does our tree look like? Maybe it looks like this. And now some of these nodes belong to U1, some of them belong to U2. Let's just say that k is equal to 2, so we'll have only two sets U1 and U2. And let's now say, okay, we have the red ones and we'll have the blue ones. Now what we are saying is that let's say all of the blue vertices or all of the red vertices are already connected. Let's maybe start with a case that all of the red vertices are already connected. So here, by the way, this means that this is both in U1 and U2. Now, how do we make sure that now all blue vertices get connected to the red vertices? Well, we just go up the tree. Well, either we have something like we have it here, where there's nothing that we have to connect anymore. This red vertex and this blue vertex are, well, this is both a red and a blue vertex. But if we now add, for example, this edge here and this edge here, then suddenly all the blue vertices are connected to red vertices. Same here and same here, because this blue vertex is already a red vertex. So we only go up in this tree. Now let's do the same thing with the red vertices. How do we make sure all red vertices are connected to blue vertices? Well, here and here this is trivial because they are already connected. But now what we can do is we can again go up the tree, and then sooner or later we will actually be connected to a blue vertex. Okay, here this you should be aware that this blue edge doesn't count for connecting red vertices. this blue edge only counts for connecting blue vertices. So we are now choosing these red edges to connect the red vertices to blue vertices of the root. And we're choosing these blue vertices to connect these blue edges we're choosing to connect the blue vertices to the root or to red vertices. And well, here we don't have to choose anything. And now what you'll see is that in this tree, we'll choose each edge at most once. We will choose it exactly once unless the vertex, the lower end of the edge, actually the lower end point, has multiple colors, then we're not using this edge at all. If it has only one color, then the edge will get exactly this color. And this now tells us that we can bound the sum of these connections, connect ui to all other uj. This we can bound by saying, okay, take the sum of these edges where, as I was saying, we're counting an edge only if its lower endpoint is only in one of the sets. Another thing is, okay, here actually each v appears only once. Each edge is counted only once, or at most once, and this means that the cost that we're seeing here is at most the cost of a minimum spanning tree that we had on this on these sets U1 through UK. Good. So as I was saying, we've seen this kind of an argument before, namely when we were talking about Steiner tree in online Steiner tree in probabilistic models. There we were saying, okay, how expensive is it to connect this one vertex to the other vertices? Now we're saying we're doing a similar argument, but we're now talking about the union, where we're talking about sets of vertices rather than just connecting a single vertex to some other vertices. But the idea is just the same. Well, what is a little smarter here is that somehow this, you now get these paths which connect you, and these paths only stop when you reach a point that you wanted to reach. So for example, here the path stops because you reached a point that you wanted to reach. Here the path goes all the way to the root. Here the path doesn't even start because you're already at a good point, namely at a point of the other color. Cool. Now let's use this very simple bound to analyze our second stage. What's our cost in the second stage? Our cost in the second stage is nothing but how much we'll have to pay for augmenting a spanning tree from S1 through S lambda so that also T is connected to this. Good. So this is what we want to understand. And what we'll now use is the fact that S1 through S lambda, they are all drawn from the same distribution as T. So we'll consider the following equivalent random process. What we'll do is we'll draw U1 through U lambda plus 1 from the distribution. And then what we'll do is we'll draw some capital K uniformly from 1 through L plus 1. And now we'll set T to be UK S1 through SL to be the remaining sets. Why can we do this? Well, S1 through S lambda, they are all drawn from the same distribution as also T. So rather than saying, okay, I first draw S1, then I draw S2, and so on, and then nature draws T, let's first draw all these lambda plus 1 sets all together. And then let's say, okay, one of these now turns out to be T, the others turn out to be S1 through S lambda. And now we can of course write the expectation of delta of S1 through S lambda comma T. This is nothing but the expectation of delta of the union of all j which are not equal to capital K, UK, comma, uj, comma, UK. And now we see, okay, this capital K, this is actually just uniformly distributed on 1 through L plus 1, so we might as well write out this expectation here. This is just the average of all these delta of the union of the uj, comma, ui. And how big is this? Here we have exactly what our lemma was bounding for us. And so we can bound this by the cost of a minimum spanning tree on the union of U1 through U lambda plus 1. Good. So this tells us now that the expected second stage cost is how much? Well, it's lambda times what we have here. So, and this is something that we can bound via this. So the expected second stage cost this will be at most lambda times 1 over lambda plus 1 times, well, let me first write the expectation, the weight of a minimum spanning tree on U1 through u lambda plus 1. So I have lambda over lambda plus 1 times the expected weight of a minimum spanning tree on u1 union and so on union u lambda plus 1, where all of these are draws from our probability distribution, which determines the terminals. So how big is this? What's the weight of a minimum spanning tree on u1 union and so on union u lambda plus 1? Well, we can amazingly do the same argument. Namely, we can say, okay, take the whatever the optimal policy would do if the terminal set were u1 and so on. What would it do if the terminal set were u lambda plus 1? All of these we are now combining. This is again a feasible spanning tree, and this is a minimum or feasible Steiner tree. This is a minimum spanning tree, so there will be at most a factor of 2. This is exactly the same argument that we saw for the first stage. Cool. Now we can see that we have this subadditivity property here, because edges just might appear multiple times in this sum. And of course, here this should be E star subscript UI, and those we can again bound. Well, we can see that those are exactly the expected second stage costs. So this tells us that the expected cost that we incur in our second stage, this is at most lambda over lambda plus 1 times the expectation of, and now we can plug in this, so we'll take 2 times the weight of what the optimal policy does in the first stage plus 2 times the sum of these. Let's now use linearity of expectation. And what is it that we're getting here? Here we are again getting the optimal second stage cost. Well, it is actually not the optimal second stage cost. It is the optimal second stage cost divided by lambda. This is something that I should have mentioned earlier, that of course in the second stage the optimal policy pays lambda times the respective weights. And this is what helps us now, because what is it that we're getting here? this will be now lambda plus 1 times the expectation of the weights of the edges for the second stage of the optimal policy. And now, this is not as nice as before, because it's not necessarily the cost of the optimal policy. But fortunately enough, we have this lambda over lambda plus 1 here. And this now helps us replace this lambda plus 1 by lambda. So this here is at most 2 times the weight of what the optimal policy spends in the first stage plus lambda times the expectation of the weights for the second stage. And this is exactly 2 times Z star. Good. So this analysis of the second stage gets easy as soon as we have the lemma, which helps us bound the sum of these deltas, and as soon as we've realized that actually we can use again the fact that these S1 through S lambda are distributed the same way as T. So if we instead first draw lambda plus 1 sets and then only say one of them will be T, the others will be S1 through S lambda, then suddenly we see that okay, this expectation that or the expected cost that we have to pay corresponds to exactly what we were bounding by this lemma. Namely, how expensive is it to augment a spanning tree? And now we're crucially, again, exploiting the symmetries. Cool. Then this other part, there's actually nothing fancy about this. Well, it is fancy, but all of this we've already seen in the first stage. All these arguments are just exactly like what we were doing in the first stage. As soon as we've come to this point, we're doing actually nothing different than what we were doing in the first stage. If you are a little more careful here, then you can actually also get this working for other number of samples than exactly that you're drawing lambda times from the distribution. This is a very nice exercise to help you once again go through this proof. And then what you realize is actually that you can also, even if your lambda is not an integer, you can actually still do these kinds of things, namely by, I think it was rounding lambda down to the closest integer, or rounding it up, I forgot honestly, but you will easily figure out that this still works, that this entire approach. Good. So we've seen that for this two-stage optimization, you can actually also choose a very different approach than solving these linear programs. There are some pros and cons to both approaches. The advantage that I see for this approach here is, besides its clarity and its beauty, that we only need sample access to the distribution. We only have to draw from each of the distributions a couple of times, and that's it. A negative aspect, though, is that, well, this is all only working with this lambda inflation factor. So what we cannot capture here is that some things get much more expensive in the second stage, whereas others just cost the same in the second stage. This was possible in the LP approach. And also something that was possible in the LP approach was that, or that is a downside of this approach, is that here the running time will depend on lambda. So we haven't actually talked about what reasonable values of lambda are, and maybe you can even show that if lambda is huge, then what you want to do is really just get everything covered in the first stage, and then you could choose an alternative algorithm, things like these. But this is certainly not reflected so far in all these calculations, so the running time grows with lambda. And this is also different in the approach that uses LPs. There, the running time, well, there isn't even no lambda, and the running time, well, does depend on the weights, just because solving LPs depends on the size of the numbers that you see in the LP. But you don't have this linear growth in the size of the numbers, which you will have here. Good. So I hope you like this algorithm and approach as much as I do. As usual, please let me know if you have any questions. I hope to see you next time. Bye for now. Stay safe.